to Life with David. I'm David, and today I'm continuing my research into the programmable input-output features of the RP2040. Last time, I built and demonstrated a velocity sensor for playing a MIDI note using MicroPython. This time, I want to make a standalone MIDI controller. Oh, really? Okay, headshot take 2.
Nope, you can't.
Why are you interrupting me, and why can't I?
I'm interrupting you because you don't know enough about PIO interrupts.
What's to know? Set, wait, and clear.
No, there's a lot more than that. State machine versus PIO versus NVIC. Multiple state machines, identification, callbacks, even state machine synchronization.
I didn't know, and I need all that?
Not all of it, but it wouldn't hurt.
Well, okay. I guess I need to know some more of the gory details. So, why don't you join me as we dive headfirst into the RP2040 PIO interrupt schemes? All modern processors use interrupts. They allow cores to attend to various tasks in a timely manner without constantly checking on their status. The RP2040 is no different. In fact, because of its GPIO and PIO, it may rely on interrupts even more. There are 26 ARM core interrupts for timers, pulse width modulation, USB communications, flash memory, PIO, DMA, GPIO, core single cycle I/O access to the bus interface, clocks, SPI, UART, analog to digital conversion, I2C, and the real-time clock. They are controlled by a standard ARM Nested Vectored Interrupt Controller, or NVIC, which is a way of enabling, disabling, identifying, and acknowledging various interrupts in a user-defined priority. Today we're going to limit our journey to only PIO interrupts. Why would we use PIO interrupts? An example is my homebrew video interface, which was featured in PIO episode 12. Here, state machines use interrupts to communicate their status to other state machines and the core. This means the PIO can complete complicated processes on its own with almost no assistance from the main core. There's a lot of documentation regarding PIO interrupts, but it's in a lot of different places. I'll put a link to all the documentation I used in the description below. Here's what I found. There are a total of 8 hardware IRQ flags that are available to the PIO state machines. State machine interrupt requests 0 through 7 can be used by any and all of the state machines, and interrupt requests 0 through 3 can also be routed to the core through the NVIC. To show how these all work together, let's look at this diagram for PIO Block 0. One of the things that can be confusing is that there are 2 different interrupt systems, the 8 state machine hardware interrupts and the 4 NVIC PIO interrupts for the ARM core. There are 2 NVIC interrupts per PIO block. They're joined together using APIs or application programming interfaces. But it's important to remember that a state machine IRQ0 is not the same as NVIC interrupt 0. We'll get into that a little later. All 8 of the state machine hardware interrupt flags are located in the IRQ register, 1 bit per flag. A 1 indicates the flag is set, a 0 means it's cleared. This register is located at 502.00030 hex for PIO 0 and 503.00030 hex for PIO 1. The status can be read by reading from this address or by reading from IRQ as a structure member of PIO. A flag can be cleared by writing a 1 to the appropriate bit. There's another register where the lower 4 state machine hardware interrupt request flags are stored along with 8 FIFO interrupts, the INTR register. This register is located at 502.00128 hex for PIO 0. The contents of this register are mapped to one of the 2 NVIC ARM interrupts for PIO 0. For instance, using the appropriate API, state machine IRQ0 and IRQ2 can trigger PIO 0 IRQ0. and state machine IRQ1 and IRQ3 can trigger PIO 0, IRQ1. Those interrupts are NVIC systems interrupts 7 and 8 respectively. Another API specifies the interrupt handler for NVIC interrupts. When the NVIC processes those interrupts, the core will call the appropriate callback function, also known as an interrupt handler or ISR, which will then clear the hardware interrupts located in the IRQ register. Let's look at a few examples to see how this plays out using C, C++. Before I get started with the C, C++ programs, a couple viewers asked if I would cover the CMake process in just a little more detail. I'll do a quick review here. For more details, please see these videos. I'm using a Windows machine. After I install the toolchain as detailed in section 9.2 of Getting Started with Raspberry Pi Pico, I set up a file structure where I have all the programs I'm going to use for a given episode in one folder, and then add pico_SDK_import.CMake, an empty build folder, and a copy of my CMake list file. I modify the CMake list file by entering the name of the project here and adding the names of my main C and PIO programs that I want to compile under target sources. Then I open the Visual Studio Developer command prompt and navigate to the empty build folder. Next, I type CMake-G nmake makefiles $. After a few moments, the build folder is partially filled with the files that are needed for the nmake process. Then I type nmake and the programs compile and build. This gives me the .uf2 file that I load into the Pico. One shortcut I take is that I copy each file I want to compile into the same C or PIO file. This means I don't have to constantly edit the CList file, just change the file names. We'll do 4 demonstrations using C, C++. In Demo 19A, I demonstrate how to identify and clear PIO interrupts 0 through 3 using an interrupt handler or callback function. Let's go through the PIO program first. This program turns an LED on for half a second and then turns it off for half a second. Then the program sets an interrupt and waits for the handler to clear it. First, we identify the PIO program name and label the start of the program. Then turn on the LED using the set command and load the X scratch register with 31. This will be the number of times we'll increment through the delay loop. We enter the delay high loop where we first execute a no-op using 30 clock cycles and then check to see if the X register is 0. If not, we decrement the X register and then jump back to the start of the delay high loop. This loop will take half a second to complete. When the X register has counted down to 0, we use the set command to turn the LED off and load the X scratch register with 31 again. Then we enter the delay low loop, which works just like the delay high loop before. After half a second, we jump into the interrupt request stall part of the program. Here we execute a no-op, which is used as a switch debounce for later demonstrations, and then set a state machine interrupt. This is a wait interrupt where we stall PIO program execution until the state machine interrupt is cleared. As we discussed before, setting the state machine interrupt loads a 1 into the appropriate bit of the IRQ register and the INTR register. Using the PIO set source API, which we'll define later, the INTR register is mapped to the NVIC, which then interrupts the main program and invokes the handler. After the handler clears the state machine interrupt, the PIO program continues and jumps to the program start again. Now let's look at the helper function used to configure the PIO program. After we invoke c.sdk and include the clocks library, we define the helper function. The main C program will pass the PIO block, the state machine, the offset of the PIO program in memory, the base number of the LED pin, and the state machine clock frequency. For more information, please see my PIO episode 7. I'll put a link in the description below. Then we grab a default configuration, map the state machine set pin group to one pin starting at pin, connect the GPIO to the PIO, set the pin direction as an output, set the state machine clock frequency, load our configuration, and then start the state machine. That's it for the PIO program. Now we'll turn to the main C program. Here we include the required libraries and programs, including the PIO program we just wrote. Then we'll define the PIO block and state machine variables and the NVIC arm interrupt number. This number will be assigned by the APIs later in the main program, but the numbers are defined in section 2.3.2 of the RP2040 Datasheet. The NVIC PIO numbers are 7, 8, 9, and 10. Next, we define our callback or interrupt service routine. This is also known as the interrupt handler. Here I print out the value of the IRQ register. I get this by grabbing the IRQ, which is part of the structure of the PIO block. This expression can be used to determine the state machine interrupt flags during the interrupt callback or during a polling routine. Next, I'll determine which state machine interrupt fired. I'll use the PIO Interrupt Git command. This command, along with others, are found in the Hardware PIO API. I'll put a link in the description below. This will return true if the specified state machine interrupt is set. If that state machine interrupt is set, then I will print out the state machine interrupt number, the value of the INTR register, and the value of the IRQ register. Then we'll clear the state machine interrupt using PIO Interrupt Clear. Next, I'll print the state machine interrupt number, the INTR register, and the IRQ register again. Then we exit the callback function. If that wasn't the state machine interrupt that fired, then I'll check for the other state machine interrupts. I know this is clunky, but I did it this way for demonstration purposes. You could also use a case or other method to check the status of the state machine interrupts. The next function configures the PIO program and assigns the interrupt handler. Here we assign our PIO number. This will be called out in the main routine using the variable PIO num. We'll also assign the NVIC interrupt number to use. In this case, the number is between NVIC interrupt 9 or 7. I could have also chosen NVIC interrupt 10 or 8 by choosing PIO 1 IRQ 1 or PIO 0 IRQ 1. Next, we add the PIO program into the PIO program memory and get the program start offset. We'll need that value later when we instantiate the state machine. Then we assign the blink LED to GPIO pin 0. The state machine clock frequency is set at 2000 Hz, which is just about as slow as it will go. We do that so we can see the LEDs blinking. Then we claim a spare state machine and instantiate the state machine using the helper function. Now that the state machine is running, we will enable state machine interrupts for the given PIO block. We can do that in two ways. We can either enable each state machine interrupt individually using PIO set IRQ0 source enabled, or we can use a map to enable many state machine interrupts at once. Let's go through the individual enabling first. We can map our state machine interrupts to either PIO interrupt 0 or 1. This can be confusing. The PIO interrupt number is just an enumeration for the NVIC interrupt number. For instance, PIO 0 IRQ 0 is the same as NVIC interrupt 7. It's done this way to make it less confusing. I'll let you decide. Anyway, in this API, we specify the PIO block, the enumeration for the state machine hardware interrupt, and whether to enable or disable the interrupt. The enumeration for the state machine hardware interrupt can be found in the hardware PIO API. This includes not only the state machine hardware interrupts IRQ 0 through 3, but also 8 state machine FIFO status interrupts. We can use a map to enable multiple interrupts in one statement. As you can see from the INTE register map, the state machine interrupts 0 through 3 can be enabled by writing a 1 into bits 8 through 11. The map to enable all state machine interrupts only would be 1111 0000 0000 binary, F00 hex, or 3840 decimal. We'll put the mask here. Next, we'll assign the exclusive callback function for the NVIC interrupt. In this case, we'll assign the function PIO IRQ that we defined earlier. Then we enable the NVIC interrupt. Now we're ready to go. We'll enter the main routine, initialize a standard input-output routine so we can output our results, and then wait 20 seconds so that I can start my terminal program, PuTTY. After I print the start of the program, I'll enter the PIO instantiation routine using PIO block 0 and then output information about the PIO, state machine, and the NVIC interrupt number. Then we enter our endless loop where we print out a watchdog timer 5 times a second. Let's try it out. First, I'll set the interrupt as IRQ 0. After I compile and link the programs, I'll drag the UF2 file into the Pico. Then I start the terminal output program. In this case, I'm using PuTTY. After a few moments, the output starts. Let's examine it. Here we output the PIO block number, the assigned state machine, and the NVIC IRQ number, which is 7. Then we look at the watchdog timer, which outputs 5 dots per second. Here we see about 1 second before the interrupt fires. The IRQ register is 1 decimal, which is 00000001 binary. The 8 state machine interrupts are mapped to the 8 bits of this register, with IRQ 0 being the least significant bit. This indicates that state machine's IRQ 0 fired. Then we print out the IRQ and the INTR registers in hexadecimal, both before and after clearing the interrupt. The INTR register has the 4 state machine interrupts located in bits 8 through 11. You can see how the bits have been cleared after the callback function processed the interrupt. This then repeats about every second. Okay, let's go through the state machine interrupts 1 through 3. Note how the value of IRQ and INTR change. These are values you can use to determine which interrupt fired. Now let's try state machine interrupt 4. As you remember, this IRQ is not routed through INTR and as such doesn't trigger an NVIC interrupt. As you can see, the LED flashes once and then hangs. How can we get the status of the state machine interrupts 4 through 7? Since an NVIC interrupt doesn't fire, we can't use a normal callback routine. However, we can use periodic polling. The PIO program is the same, but we modify the main C program like this. I'll change the callback routine to a polling routine. I'll use the same tests on the IRQ register to see if interrupts 4 through 7 fired. If one did, then I'll print out the value of the IRQ and INTR registers, clear the interrupt, and print the IRQ and INTR registers again. In the PIO configuration, I'll eliminate all the callback assignments. And in the main program, I'll call the polling routine every 200 milliseconds. Let's try it out. We'll start out with IRQ4. Here you can see that it does not register in the INTR register, but does register in the IRQ register as 10 hex. Note that the IRQ register clears after the polling routine completes the clearing API. Let's try it with IRQ 5 through 7. The results are as expected. The IRQ register shows the state machine interrupts 4 through 7, and the INTR register does not. Okay, we've triggered all the interrupts on one state machine. Can we run all the state machines and determine which one set an interrupt? Yes, we can, using the relative mode of the state machine interrupts. In this mode, the two least significant bits of the IRQ number are replaced by the two least significant bits of the addition of the state machine number and the IRQ number. Here's a table that shows the resulting IRQ indices and the resulting IRQ register flags. The next program demonstrates the interrupt identification across multiple state machines. In the PIO program, we use relative mode with the interrupt statement. The main C program is similar to Demo 19A, except I assign 4 state machines instead of having the API select one of them for me, and then instantiate the 4 state machines at 250 millisecond intervals. Each state machine will run the exact same program but has its own LED. Let's try it out. I'll start with IRQ 0. You can see how the IRQ number changes as each state machine sets IRQ 0. Here's the interrupt indice number progression for IRQs 1 through 3. We can synchronize all 4 state machines by clearing a common interrupt. In demonstration 19D, I set up the PIO program to continuously blink the LED on and off. A switch is added to jump out of the blinking loop and into an interrupt and wait segment. Here the state machine will stall while it waits for that interrupt to clear. The changes to the PIO program include adding a jump pin command to the delay high and delay low loops to branch into an interrupt stall script, and adding a jump statement back to the start of the program at the end of the delay low loop. In the helper function, I add a jump pin into the configuration. In the main C program, I eliminate the callback function, define the jump pin, and add the jump pin to the state machine instantiation. In the main loop, I initialize a 5th switch to trigger the interrupt clear, and then pull the switch status every 200 milliseconds. If the switch is pressed, the interrupt is cleared and a message is sent to the terminal. Let's try it out. First, all the LEDs are blinking out of sequence. Then I stop them one at a time by pressing the switch assigned to each state machine jump pin. Now they're all stalled. Then I press the 5th switch, which clears the interrupt, and they all start blinking simultaneously. There are a couple more considerations regarding callback functions. If there is a possibility that several interrupts can occur at the same time, the NVIC interrupt can be disabled immediately upon entering the callback routine using the IRQ set enable API. Then at the end of the callback routine, the interrupt can be enabled again. This will stop interrupts from stacking up on top of each other inside the callback routine, which could cause problems. It's very important that the callback routine be as short as possible. One thing I investigated for the last demonstration was to use a callback function which would stall until a switch was pressed. The Pico immediately crashed. So I tried seeing how much of a delay I could put into the callback function. It turns out not much. Here's a demonstration 19C with a 20 millisecond pause. The Pico crashes. In fact, I shortened the pause to 1 millisecond and it still crashed. I also want to demonstrate how MicroPython can handle the same interrupt tasks. However, this video is getting very long. I want to give MicroPython equal time, so I think I'll end it here. Thanks for joining me today. We examined the PIO interrupt structure for the RP2040. Using C, C++, we demonstrated how to identify and clear multiple interrupts in state machines. We also explored how to synchronize several state machines together. It took a lot longer to explain this topic than I expected, so I didn't have a chance to also cover MicroPython in this video. However, I'll be releasing a second video soon where I explain how MicroPython handles these same tasks, so stay tuned. If you like this video or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!